So we start with the afternoon sessions. Our first speaker is Julián Rincón, who is at the group of Matemática computacional.
No, applied math and computer science.
Computer science in Universidad Rosario.
Yes.
Okay.
Uh-oh. So, should I start? See? Okay. So, first of all, thank you, Alonso, for the invitation for the opportunity to give a talk here. So, what this talk is about is also facing the many-body problem or the curse of dimensionality that Roger was mentioning this morning, but we're going to attack it from a different angle. Okay, so this is like complementary to what the school is about. So, first of all, I need to thank my collaborators on this, Martin Ganal and Guy Vidal. And the work that I'm going to show here was mainly done while I was at Perimeter Institute a couple of years ago, I think. Okay, so what is it that we're trying to accomplish here? So, what I want to do is to characterize ground state wave functions, in this case for continuous quantum many-body systems. And the idea is to go beyond whatever perturbation theory can do, or mean field approaches, and so on. Right? What do I mean by characterize? I mean extract physical properties such as scaling of entanglement entropy, calculating correlation functions, and spectral gaps as well. Okay, so how are we going to accomplish that goal? So the idea is to start with giving you a brief definition of what a tensor network state is. Then I'm going to focus on a specific type of tensor network, which are matrix product states. And then I'm going to jump to the interesting part, which is the continuous version of this lattice tensor network. And I'm going to move on to how you optimize these continuous tensor networks. And finally, I'm going to give a very nice application on an extension of the Lieb-Liniger model, which I'm also going to explain. So, same as Roger was saying this morning, what is the big challenge here, right? So, what is it that is between me and the solution of the problem? Is the so-called many-body problem, or as they call it in CS, right, in computer science, is the curse of dimensionality. And that is basically, one way you can formulate it like Roger did this morning, or I can just, state a simple question like this. So if I have a quantum many-body system of n components, so the idea is how to handle the exponentially large number of parameters that I need to describe the wave function of such a system. Okay, so we need to get around this. Because as Roger was saying this morning, for n equals 50 spins, then you need a whole bunch of storage that is just not accomplishable. Okay, so that's when tensor networks get into this business. So I'm just gonna give you, like an overview of what this is about. I'm gonna try to leave out as many details as possible. So that's why I'm gonna give you this simple definition of tensor networks. So you can say that tensor networks are a reliable alternative to get around the curse of dimensionality. Okay, and I say alternative because as you saw this morning, and you're gonna see these next few days, this is not the only alternative to try to solve the many-body problem in the quantum realm. Okay, so tensor networks, what are those? They are a class of variational ansatz that offer an efficient parameterization of many-body wave functions, right? And the idea is that from those many-body wave functions, I'm going to be able to extract observables in an efficient way. Okay, and what do I mean by efficient? I mean, like Roger again was saying this morning, use sub-exponential resources. And in our case, that's going to boil down to using polynomial resources. Okay. Hopefully, in the next slides, this is going to get clearer. Okay, so like I said before, what I want to do here is to talk about many-body wave functions. So for the sake of concreteness, we can think of a one-dimensional spin one-half system, right? Where in each local site I have a spin, and that spin has 2 degrees of freedom, right? Up or down. Okay, so if I build a basis using a tensor product states of those n spins, then I can write down an element on that basis like this, where this I1 number labels the state of spin at site 1, and so on and so forth until the number n. And then I can write down in the Hilbert space that is defined by this basis, I can write down any vector state like this, right? And this is some basic linear algebra, right? So I build a tensor product state, form a basis of the many-body system, and then I can write down any vector in that space. In this particular case is a Hilbert space in this form, right? And in order to be able to completely characterize this wave function, if each of these sites takes 2 states, then I'm going to need an exponential number of parameters, right? Like 2 to the n of those parameters. Okay, so to make things a little simpler, so in tensor networks, what we do is to, instead of dealing with this object all the time, we use a diagrammatic notation. So what I'm going to do here is abuse a little bit the notation, and instead of writing this whole vector, what I'm going to do is to describe these weights, these amplitudes, using this drawing. Okay, and you can think of this object as a rank n tensor, right? So I have each of these legs represent the possible values that these values in, ij, i1, i2, and so on can take, right? So each of these legs sticking out here can take 2 different values, okay? So this is a rank n tensor because I have n legs sticking out of this object, okay? And the idea in tensor networks is that, yes, we need 2 to the n coefficients to describe this wave function, so we need to scale that down in such a way that we only need a polynomial number of parameters, but still be able to describe these 2 to the n coefficients of the wave function, right? And that's when these matrix product states come in, which is a specific type of tensor network. And what we do with matrix product states is that instead of writing down this huge tensor, what we're going to do is to decompose this huge tensor in a product of small tensors, like the ones that I'm showing down here. So you can think of this bubble with these 3 legs sticking out as a tensor of rank 3, right? So this leg sticking down is still the physical state, right? So is the state that the spin at that particular site is going to take, up or down. And then I have this extra parameter, this extra parameter here and this other parameter here. And then I have the freedom to choose how large the tensor is in this direction if you want. Okay, so I have 3 dimensions here. One is this one to the left, this other one to the right, and then the physical index sticking down. Okay, and the difference is that if I start counting parameters in this picture compared to the parameters that I have in this picture, then I can realize that the number of parameters that I need is linear in n, right? Because if I take one of these tensors and then I multiply, and then I calculate the number of tensor entries in this tensor, then I have 2 here because this is a spin 1/2 system, so I have two possible states. And then I have these 2 legs, which each one taking at most d parameters, so you get d times 2, right? So this is why you have 2 times d squared, right? And how many tensors of those you have? In principle, you have 1 tensor for each spin site, so that's why you have n of those tensors, and then at the end of the day, you have a linear in n number of parameters to describe this whole wave function, okay? So as we saw this morning, that if I'm trying to solve the many-body problem exactly, then I'm going to have to deal with an exponential number of parameters. Here in tensor networks, what we do is to reparameterize the wave function in this particular way for the case of matrix product states. And then you can see that we can go from something that is not very useful because it has an exponential number of parameters to something that might be, and it has proven that is very useful because I have a polynomial number of parameters in the number of components of this many-body system. Okay? And just so you know, this parameter d is something that I can tune by hand. So of course, the larger d is, the more exact is my approximation. Okay? But of course, the more computational resources I'm going to need. Okay, so in that sense, this set of ansatz are said to be quasi-exact because I only have one tuning parameter, and with that, I can reach the exact solution if I have enough computational power. All right. So of course, I have to pay a price here, right? Nothing is for free. So if I go from this general viewpoint, to look at a vector state in Hilbert space, from this view to this other one, then I have to pay a price. And the price is that with this prescription, I cannot represent any state in Hilbert space that I want, just a few candidates. But the good news is that those candidates are the ones that I'm looking for, right? So I'm going to be able to represent with good accuracy ground states of local Hamiltonians in one dimension if I use an ansatz like that. Okay, and this is what I'm going to show you when we get to the results.
I don't get it really good. Why each bubble is a rank 3 tensor?
Because you have 3 legs sticking out, right?
Because the number of inputs.
Yes, exactly.
Okay.
That's why this guy is a rank n tensor, because I have n legs sticking out. The thing that I forgot to say is that if you see this line, if you see that 2 circles have a line in common, that means a contraction. So that's why you don't clearly see them here. But if you isolate one of these bubbles with 3 legs, then you just get a rank 3 tensor. Okay, yeah, thank you for the question. Okay, so another way of looking at this is with this drawing. So this was done by Guifré, so here's the reference in case he complains. Right, okay, so the idea is that you have the exact representation. So this bubble, this orange, I think, bubble represents the whole Hilbert space of the n-spin 1/2 system. Then I can write down any vector state in that space like that, right? So I think that's clear. So, right, this is the same tensor product state basis that I was mentioning before. And then I can write down anything that I want like this in that Hilbert space. Right? In tensor networks, what we're doing is that when we reparameterize the wave function like that, then we are only describing a small corner of the whole Hilbert space. Right? So I have an exponential number of states here. And with this parameterization, I'm only addressing a small subspace of this huge Hilbert space. But the good news is that that small Hilbert space, that subspace, is exactly where the ground states of local Hamiltonians and some other conditions live in. Okay? So that's why if I start tuning this chi parameter, which is the same as this d parameter here, then I can start getting more and more accurate representation of this object. Okay, so that's the idea. So if there's something that I would like you to take home, is the message in this picture, right? So with tensor networks, we only represent a small corner, but it's the interesting corner because ground states of local Hamiltonians live right there. Okay? And again, right, this is storage-wise. This I cannot store in a computer for 100 spins, but this I can because I only need a linear number of parameters in order to represent the wave function in this form. Okay, and this is called a matrix product state because if you fix the configurations of each spin on each side, then you just get a product of matrices, right? So that's why it's called matrix product state. So this is like the summary, right? So I write down the state, like that in general, and the amplitudes have this specific form, and diagrammatically it will look like that. And this connection from this side to the other side means that I'm using periodic boundary conditions. Okay, and something that I'm not interested in improving here, but I just want you to know, these kind of ansatz provide a non-perturbative approach to tackle the many-body problem. And all properties such as scaling of entanglement, decay of correlations, and so on can be established through the structure and connectivity of each tensor network. Okay, and if somebody is coming from the computer science side of this business, then you can think that the abstract data type that I'm trying to represent here is the many-body wave function, right? So I'm trying to get the many-body wave function. I'm trying to get observables out of these many-body wave functions. And the way I implement it would be the data structure, right? And those are tensor networks. So one example are these matrix product states, but other data structures that try to represent this abstract data type are projected entangled pair states and multi-scale entanglement renormalizations ansatz, and there are some others, right? And each of these data structures have a different representation invariant. So if somebody comes from the CS side, maybe they can understand what these objects are in terms of this slide. Okay, and now we go to the continuum, right? Now the idea is to take an ansatz like this and start refining, right? If you think that this is a lattice spacing, this distance from this tensor to this tensor, then I want to take the continuum limit of that lattice spacing and get a new ansatz that is going to allow me to explore quantum field theories in 1+1 dimensions without using perturbation theory, okay? So if I do that, I can define this continuous version of matrix product states, and it's the same business all over again, right? So these are variational wave functionals this time, because I'm trying to describe field theories, but it's the same business as before, right? Efficiency all over the place, right? In the parameterization, in the extraction of observables. And the idea is that this new variational class is going to allow me to describe field theories in 1+1 dimension. How do I build such an object? There are 3 specific ways of doing it. So I just take a specific class of these matrix product states, and then I start taking the continuum limit wisely. So if somebody is interested, I can tell you about it. But you can also define a continuous matrix product state considering the non-equilibrium dynamics of a 0-dimensional theory, or as the solution of the quantum Gross-Pitayevsky equation. Okay, and here are the references if you are interested. So this is just a quick slide that tells you how to write down these matrices that form the matrix product state in terms of the lattice spacing parameter epsilon, and some new matrices that are going to be the ones that I'm going to optimize in a potential algorithm, okay? And then the idea is that if I have this specific form for the matrices A0 or A up and A1 or A down, then I can take safely the continuum limit and end up with a specific object, which is the continuous matrix product state. So once I have these ansatz, how do I optimize them? So you have 2 options. You have what is called the time-dependent variational principle. And the idea, at the end of the day, what I want to do is to integrate numerically Schrodinger's equation, either in imaginary time or real time. In this case, I'm only interested in imaginary time because I want to get the ground state. So basically what I do is to integrate by using Euler or some integrator scheme. So given the vector in the current time, then if I am able to calculate this product, the Hamiltonian times the vector at that same specific time step, and take this linear combination, I will get the next version of the wave function in this time tau plus delta tau. Okay, so what time-dependent variational principle does is to give you a prescription of how to calculate this specific object, which in terms of vector spaces, this guy lives in the tangent space of the variational manifold, and this variational manifold is defined, of course, by the matrix product states. Okay, but something that we did with Martin and Guifrey was to propose a new way of optimizing these matrix product states, and is not using this time-dependent variational principle, but just using good old energy minimization. So this is the cost function, and all you're doing here is just taking a steepest descent approach to get the corresponding matrix elements that describe the wave function of the many-body system of interest. Right? So this psi is a matrix product state. This H is the local Hamiltonian that you're interested in, and then this is your cost function, and then you're trying to minimize in terms of these matrices Q and R, or A1 and A2. And then what you do is you have a landscape, right, in terms of this of the parameters that describes each of these matrices, and then you take small time steps downhill, and hopefully you will get to the global minimum. Okay, so what is the advantage of this method over the old one is that we can get way more accuracy in much shorter times. Okay, so what I'm showing you here is this is the field theory that we are trying to get the ground state out of, right? So I have a non-relativistic quantum field theory. This is called the Liebling-Egger model. So this psi daga is a field operator, a bosonic field operator that creates a boson at site X. You know, this psi is just the annihilation field operator, and then I have this interaction right between bosons, and you pay a price G if you encounter two bosons on the same site. So if I try to calculate the ground state energy as a function of the iteration in this scheme, right? If I take steps and go calculating the expectation value of the Hamiltonian, then I get a plot like this. So this green line is what you get if you do TDVP, and this blue line is what you get if you do just gradient optimization or energy minimization. And you can see, you know, that you can get the same accuracy as TDVP 50 times faster, right? And because these have an exact solution, we can compare to the exact solution, and then you can see that both go to the exact ground state, but with this gradient optimization, we do it 2 orders of magnitude faster. Again, this is just another way to remember this parameter D that tunes the accuracy of the approximation. Then we can calculate the ground state energy as a function of this parameter that has to do with the interactions between bosons. And then we can see, maybe not here, but here in the correlation functions, that as I increase the number of variational parameters, then I get better accuracy at long distances. Okay? So this plot just shows you that continuous matrix product states are a good variational ansatz to describe quantum field theories in a non-perturbative way. Okay? So that's the take-home message from this slide. Okay? And now what we can do, now that we have proven that this ansatz is really good for these non-relativistic quantum field theories, is we can now try to generalize this Hamiltonian and try to explore new models that haven't been explored before. Okay? So one model that we proposed in another work with Martin and Kifre was to just change the interaction and make it like quasi-long range. So I'm going to write down the interaction between bosons like this, parameterized by this function. And then you can see that if I choose the interaction function like this delta, then I recover the Liebling-Egger model like this. You see there's only one integral, and it's an ultra-local interaction. So this is what you get if you parameterize W like this. And what we are proposing now is to extend this interaction to be exponentially decaying. So I have this new parameter eta that tells you how deep is the interaction between bosons. Okay? And what is interesting is that this specific form of the interaction, it's an interpolation between this ultra-local version of the interaction between bosons and what is the so-called soft-Coulomb interaction, which is the regular Coulomb interaction but regularized at short distances by this parameter D. So this specific interaction is like an interpolation between these two. So what we did was to write down the Hamiltonian with using this particular function and optimize and try to get the ground state and explore the phase diagram of this model. And this is what we get. So on the left, I'm showing you correlation functions, in particular superfluid correlation functions and charge fluctuation correlation functions. And you see that for weak coupling, that is when this parameter G is small, then the superfluid correlation functions are the ones that dominate. And a strong coupling, that is when the interaction between bosons is very large, then the ones that dominate are these charge fluctuation correlation functions. They dominate over the superfluid state. And then what I can do is to characterize the way this correlation decays using an exponent, which is called the correlation exponent. The name is not really important now. The important thing is that I can characterize the decaying of this correlation function using that parameter that I call K. And this is how this parameter looks as a function of the interaction strength, okay, in the weak and strong coupling. So you see here that this K is larger than 1 for weak coupling and is smaller than 1, sorry, for strong coupling. And what does that mean? What it means is that if I try to draw the phase diagram of this extended model, then I get, for large values of K, then superfluidity dominates, and for small values of K, I get this new phase that wasn't seen before, which is a quasi-crystal state. Okay, why is a quasi-crystal? Then I can tell you about it later. But the point is that we get, by extending this linear model, we get this new phase, which is this quasi-crystal state. And there is some phase in the middle that is not that interesting for our purposes. But the important point is that you get two different states and therefore a quantum phase transition between those two states. In the regular linear model, you just get superfluidity. So this parameter K is never smaller than 1, so you always get superfluidity. Okay, but with this extended linear model, you get these two new states, and therefore this is like the simplest model in the continuum that gives you a non-trivial quantum phase transition. And because of these continuous matrix product states, we were able to extract the phase diagram of this particular model. Okay, and this is just to show that there's some universality. If you rescale things properly, then at weak coupling, you recover what you know from linear model, and at strong coupling, then you get this new phase, and that's why this parameter K is smaller than 1. Okay, but this is what this plot is trying to say. Okay, and then just to conclude, let me just say that tensor networks are an efficient strategy to attack the many-body problem. And in particular, I hope that I convince you that these continuous matrix product states are a powerful ansatz to describe non-relativistic quantum field theories in 1+1 dimension. And I think I also showed that this gradient descent optimization procedure that we propose is like between 50 and 100 times faster than imaginary time evolution. Okay, and lastly, this extended linear model is a simple continuous model with a non-trivial quantum phase transition between a superfluid and a quasi-crystal. Okay, thank you. Pregunta.
Why is great energy ionization faster? Like, is there a physically motivated answer?
Yeah, the way that I see it is that if we go back to the form of the matrix product states, then when you do, you have three different vector spaces for each tensor, right? One is the physical vector space, and then the virtual vector spaces that are described by the indices here and here. Okay, so if when you do imaginary time evolution or TDVP, you are forced to, this space is orthogonal, and in TDVP only this space, this subspace can be orthogonal, and this space is not necessarily orthogonal. So when you are exploring all the configurations and calculating the energy, then you are exploring probably the same direction more than once. Whereas when we do this, the energy minimization algorithm, all these three spaces are orthogonal. So each time you advance in a significant way. right? Just because you get the freedom of choosing this subspace orthogonal, and this one is by construction.
So, but do you discretize, or are you using?
No, this is directly in the continuum, but we just write it like that because picturing it is simple. So yeah, that would be like the reason for that speed up. Yes.
So you have a phase in between the crystal one
Yes.
and the superfluid one. How do you distinguish it? It's super.
I just distinguish it because I know that this one-dimensional model at low energies can be described as a Latinger liquid. Okay? Because the Latinger liquid is a fixed point in 1 + 1 dimensions. So I know that at low energies, I can rewrite this Hamiltonian as this specific theory. And from those, using conformal field theory, you can extract the exponents of the correlation functions. And then you can tell that there are 3 different regimes. One is when this exponent is larger than 1. The other one is when it's between 1/2 and 1. And the other one is when it's below 1/2. So it turns out that if you look at all the relevant correlations, you see that when k is larger than 1, superfluidity dominates. When k is smaller than 1/2, then this quasi-crystal state emerges. And then in the middle, there is this Tonks-Girardot state that happens when the interaction is very large. And then you can show that if you are just below this Tonks-Girardot line, then you can map that to hardcore bosons with an attractive interaction. And that's what people call the Tonks-Girardot state. But it's basically just by looking at the correlation exponents that you can tell between the 3 different states. But it's something very particular to 1D. Yes?
So how does the scaling of the bond dimension work with the lattice size? I mean,
With the lattice side, no, I can safely take the continuum limit for fixed bond dimension. I can take the continuum limit, right?
okay, so you fix D and then you take the continuum.
I can take the continuum limit, and there's no issue there. The only issue there is that now.
Do these limits commute? I mean, if you any problem if you. I mean, like.
Well, we don't really want to take the continuum limit. You mean what limit in the bond dimension? D goes to infinity?
Yeah, I guess I don't know. I mean, you could think of situations where like the correlation length that diverges or close to a point or something like that.
No, what you typically do is to let D fixed, then take the continuum limit, and then once you have the continuum version of the matrix product state, like systematically increase the D, and then approach the critical point if there is one.
So you told us the bubbles are a tensor of rank 3 because of the inputs, and one of these inputs are the spin 1 or -1. But if I want to decide to use another particle which is like a 3.5 spin, how can I change the dimension of the matrix?
So what you have is something like this, right? So the dimension of this subspace is D. This one I have also D. And here is the physical dimension that I'm going to call small d. So if you have a spin 1/2, then this d is equals 2. If you have spin 3/2, then d equals 4, right?
So
and so on.
I increase the spin I introduced.
Yeah, if you change the model, then the local Hilbert space is going to change, and that means that this number is going to change. So if you have a Hubbard model, then this is going to be 4, right? But if you have a 2-orbital Hubbard model, then this is going to be 16.
And
right?
Thinking of this, it's correct to assume or to thinking we get a different result to the phases we get. For example, not to crystal, to super TT, to superfluid, but something in between.
I don't understand the question. Can you say it again?
The spins in the input of the bubble, for example, 3.5. We can think in another phase transition in your result. Is that
Well, here, technically speaking, this D is infinite, right? Because I have soft core bosons. So this is infinite, but this is something that you get away with that because of the way the ansatz turns out to be. So if you start with, so what you typically do is to write down these matrices like that, and then this basis is written in terms of creation operators, right? And then those creation operators, then we allow them to have as many bosons as we want per site. And then for these results that I showed, I'm using D equals infinite here. Yeah.
Hi, the correlation parameter you're using, the K, is that the same as the Luttinger parameter?
It's exactly that. Yeah.
That explains why one is some sort of phase transition limit, right?
Yes. Mm-hmm. Yeah.
How do you tune the learning rate in the gradient descent algorithm? How do you assure that the algorithm is not stuck in a local minimum?
You just try several times with different rates.
Just try.
Yeah. Well, if you are able to come up with an implicit integration scheme, then you're not too worried about the